Thank you so much for the invitation. I was very nervous about coming here to give a talk in front of algebras. I'm very much a topologist, and so this is, I apologize if I'm coming at this from a different viewpoint, but it's, like I said, it's, I'm coming from a topology point of view. So in the early 1980s, there's this Jones polynomial. And from the topologist point of view, it was this thing that came from mathematical physics and just kind of landed on our laps. And I don't know where it came from, kind of, except that it was something related to mathematical physics. But it proved very quickly some things that were very hard for topologists. So for example, in maybe 2 lines, you can show that the right-handed trefoil, left-handed trefoil are not the same, which before took quite a few pages to do. It also proved the Tate conjectures, which were open for about 100 years, that said that if you had a knot diagram and it was alternating and it didn't have stupid crossings, then it was the minimal diagram, and that you couldn't draw it with fewer crossings. So anyways, there's Witten then took this Jones polynomial and he made it into a 3-manifold invariant, which was even better. We were all very excited about it. But after that first little rush of what happened, there wasn't very much to do with it, right? Like we didn't know how to use it, how to apply it. It was good at telling 3 manifolds apart, but not that great. And really the question that we really wanted to know was, okay, there's this invariant, there's a Jones polynomial for knots, the WittenReshetikhin-Turaev one for 3 manifolds. What in the world does it measure? Does it measure genus? Does it measure volume? Does it measure length? What is this thing? And the physicists gave us a whole bunch of conjectures. There's this famous one about volume conjecture, which relates to the asymptotic expansion of the Jones polynomial with the volume of a knot complement. But again, it doesn't really make sense where it comes from. So from the topology point of view, we have these really, really nice quantum invariants, and we wanted to understand it using geometry. And so one of the few places, basically we couldn't, there's very, very few results in this direction. But one of the few places where we know there is a connection is this thing called the Kauffman bracket skein algebra. It comes up in the Jones polynomial and the Wittenreshetikhin-Turaev theory, and this thing called the topological quantum field theory. It's important in there. And the amazing thing is that it was shown to kind of be related to geometry in a very, very precise way. And the more we study it, the more we know about its connection with hyperbolic geometry. So today, what I'd like to do is to kind of give a few different stories. So I'll give the story for the skein algebra of a surface. That's what we know so far. And then in the second half, I'll generalize it to generalize the skein algebra, generalize the kind of hyperbolic geometry that I do, and kind of try and mimic this first part. And then in the second part, there might be relations to other algebras that might come up. So let me see if I had it. Here we go. So that was what I wanted to say. So there's the first part, which is what we know about Kauffman bracket skein algebra and Teichmuller space, which is very important in hyperbolic geometry. And then the second one, we want to generalize it to different kinds of surfaces, different kinds of skein algebras. And then in the third part, if I have time, I'll get into more nitty-gritties. But if we don't get there, it's totally fine. And I should point out that this is joint work with Han-Bom Moon, who's an algebraic geometer, and it's been very enlightening working with him. Okay, introduction to Kauffman bracket skein algebra. So I didn't know where the background was of the audience, so I decided to go way back. So here's Jones polynomial, but it's not the Jones polynomial that I'm interested in, it's the Kauffman bracket version. They're essentially the same. The only difference is that for the Kauffman bracket, I need to keep track of this thing called the framing, which essentially means that I have to keep track of kinks, or another way of thinking about it is every point of my knot, there's a normal vector that I have to assign. So I have a variable q. The physicists tell me I should call it e to the 2 pi I h bar. I don't know why. The Kauffman bracket. So in the 3-sphere is basically you take a picture of your knot and then you apply these rules to simplify it. Okay, and it says that if you have a crossing, you can resolve it in 2 ways with some power of q to keep track of which way you turn. And then if you see a little loop then you can take it away and you put a number minus q inverse in front. So again, this is there's some kind of like vector in front. So my convention is that the vector is always perpendicular. So just an example. So here's a not very difficult knot, right? And I can resolve it, the one crossing in two ways. And in this one on the left, I have two circles. I have two factors of minus q inverse. And over here, I have one. And I simplify and I get this nice Kauffman bracket. However, if I just have the unknot, it's minus q inverse. And so what this says is that as Kauffman, as framed links, these two are different, right? And you can see that if you, I don't know. So essentially another way you can think about it is the framing means that I can't undo kinks. Okay, so that's really how I think about it. So just a quick observation. So if I'm drawing pictures in S3, after I resolve, I always get little circles. And this circles always get replaced by q minus q inverse. And so this means that whatever Kauffman bracket I have, it's always a Laurent polynomial. Now, the other observation is that if I have two links, knots, right? So here I just drew them, whatever. But when I do the Kauffman bracket of the two of them, I can resolve these ones first and then resolve these ones. They're kind of irrelevant to each other. And so I can think of the Kauffman bracket of the two of them together as the Kauffman bracket of this one times the Kauffman bracket of that one. And the other thing is that if I move them one on top of the other, then that also doesn't matter because it's an invariant. So technically I can move them apart. So I could think of this as some kind of algebraic manipulation where if I take two links, instead of putting next to each other, I could put them on top of each other. Okay, and so this gives me some kind of multiplication. Somehow I prefer on top instead of next to because this means that I can do interesting things later. Okay, so now the Kauffman bracket, I can think of all the possible Kauffman brackets that I get out of links and link diagrams in S3. And because of what I just said, I can think of this as an algebra. So again, I have this variable. I look at all possible links, right? Framed links, linear combinations of them. And then I have these relations. So that gives me the module structure. And then I think of on top of or next to whichever one you want to as the algebra structure. Again, this isn't very interesting because in S3, this is just the Laurent polynomials in Q, right? So, so I want to make it more interesting. So I'm a topologist. So topologists will say, instead of looking at knots and links in S3, look at any old manifold you want, right? And you can play the same game. So you take Q, you take all possible framed links inside your arbitrary 3 manifold, take linear combinations of them. You're allowed to remove crossings and remove circles. Anytime a circle bounds a disk, you can take it away. But then the problem is that I have a module, but I don't get an algebra structure, right? This module is important for other reasons, and people try and compute this. Actually, it tends to be very hard to compute even this module. There's only some families that are known, but there's been progress in this area anyways. So for me, this is, yeah.
Sorry for the interruption. You said you have a module, but you don't have an algebra structure. So where does the module live? I mean,
so it's just a module. So you have a 3 manifold, you can look at all the links in it and then look at this module and you just compute it.
Sorry, I don't understand. So when you talk about the module, you need an algebra structure such that this module is defined?
No, it's just a module. There's no algebra structure yet. I'll put it, for some manifolds, there's, yeah, it's a Z. It's just a vector space.
Oh, okay. Okay.
Sorry.
Okay, thank you.
Thank you for the, yeah, so this is just like, this is manifolds, right? So this is generic manifold. And like Kaveh said, this is not satisfying. We're in an algebra conference. So we want to pick a manifold where there is an algebra structure. And so if I look at the special case where M is a surface, then I get an algebra structure. So the way to think, yeah.
Sorry, just to ask you a trivial question. Why can't you just put things on top of each other like you did before?
Because there's no obvious way to do that.
Okay.
Because if like, there's no obvious, like what's on top of someone else or what's next to someone else in a three manifold. So I think that's the thing, is sometimes you can do that for specific three manifolds, but not for everyone. And also whether it descends to an algebra structure too is kind of weird. So if you have a surface, then there's an obvious thing of on top of. Okay, so what I think of is, think of a surface like, and it's hollow inside, right? So like the outside of a donut, like the outside of, or an inner tube, right? Like and then you thicken it up just a little bit. So you take a surface across the interval. And so now there's some sense of on top of, right? Because there's an inside and an outside. So you could take two things and kind of put them on top of each other. Let me do a picture. So you run the same thing, but now there's some sense of how to do the algebra structure. So for example, here's, I have an inner tube, and that little puncture there is where you blow the air in, right? Inflate your inner tube. And I have, your inner tube is slightly thick so that there's room for crossings. And I have one knot right here and a second one. And so now I can think of putting the second one on top of the first one, right? And there's a clear on top of operation, like this superposition. Next to doesn't make sense in this case, right? And so this is what I like. And you can resolve this crossing. I've resolved the first one, and then you can continue and resolve this one as well. And then I would get 4 terms. Now, the interesting thing about this is that the sense of on top of, right? So if I swap the order, now this one is on top of that one instead of the other way around. And when I resolve, these powers of Q pick up the difference. Okay, and so, oh, you can't see the bottom half. Let me see if I can, is that better? Maybe one more. Is that okay? Is it too small? It's like either too big or too small. But now these two are not the same because Q to the half and Q to the minus half aren't the same. And so I have something that's non-commutative. Any questions so far about, yeah? This is a one punctured torus. But that was because I had this little bump, this hole there. Yes, just the inner tube part, not the donut part. Everyone okay? Okay, all right. So it's non-commutative. And it was defined, I think, by Reshetikhin-Turaev. There's no topologists here, I think, so there's some issue about who did what first. But but in any case, they knew from the beginning that this multiplication was not commutative, with some exceptions when the surface is too small, right? So if you have a sphere with only one hole, or some examples. And also we knew that if Q is 1, or actually, then Q to the half is plus or minus 1. And so then Q to the half and Q to the minus half are the same. So we knew that that was commutative. We also knew that there were, like, if you put a hole around the puncture, then that commuted with everyone else, because this hole around the puncture, you can make it really, really tiny, then it'll commute with anyone else. Okay, and so that was known. And then with some extra work, Reshetikhin showed that it's infinitely generated as a module. And the reason is because let me go back, like here, these all, if I remove all the crossings here, these all are linearly independent from each other. I can't write this as a linear combination of the others. And so as soon as you have loops that don't bound disks, then you get a whole bunch of linearly independent elements. Okay, and then Bullock also showed that it's finitely generated as an algebra, and Bullock-Reshetikhin has computed the presentations of this skein algebra for a very few number, and I think it's still few. I don't think there's been much progress in that direction so far, but these presentations are really nice because they have been shown to be related to things that are very far-flung, like representation theory of UQ SO3, if I say it correctly, I'm not quite sure. But so anyways, okay. And then, so since that was what happened in the late 1990s, and then there was basically nothing. And then recently there's been like a lot of things happening with the skein algebra. So it turns out that it's a Noetherian domain, meaning there's no zero divisors. And one way to do this is to embed into a quantum torus. you could show that the center not only has these puncture loops, but it has these other things in it when it's a root of unity. You can, and I don't want to really talk about it, but you can ask me later, is that if you take a loop, then you can color it by a Chebyshev and then get central elements. And this Chebyshev is not the normal Chebyshev associated to UQSL2. It's the other one. It's the cosine one, not the sine one. So there's one that starts with 1 and one that starts with 2. This is the one that starts with. And then if Q is a root of unity, they go even further. It's finitely generated as a module of a center, and then you get these Azumaya, and then you get these people that come from rock topology. They're like, I don't know, factorization homology people. So, and there's a lot of activity recently in this direction. All right. So what's interesting here is in this slide, we're starting to see something called SL2C character variety. And this is what I'm excited about, because this is where hyperbolic geometry starts to appear, right? This is why we're all really excited about the skein algebra, because it's related to hyperbolic geometry. So now I'm going to go back to hyperbolic geometry. Any questions? Yeah.
Do you mind zooming in just a tiny bit?
Yeah, sure. If I can figure out how. Does that better?
Yeah.
Yes, okay, thank you. So any other questions, requests? Hyperbolic geometry. So now the first thing is, I no longer want to draw my pictures like this. I want to draw them like this, where there's some kind of metric and there's some links. And in particular, I want to look at the Teichmuller space, which is the isotopic classes of all possible hyperbolic metrics or metrics on this surface. And the key is that I want finite area. Okay, so that means that, for example, when I have these punctures, they kind of go out into infinity and they're like long and thin. They're called cusps. Okay, so, and the nice thing about these metrics is that if I have a loop, so loop, I can compute its length, right? Because metric length. And what else? So I'm going to define this thing, which doesn't really make sense right now, but so here's for every, if I fix the K, then for every metric, I have some kind of length for that K. And instead of just looking at the length, I'm going to do this weird thing that looks, that'll be, I'll explain why it's called trace, is minus e to the length over 2 minus e to the minus length over 2. Right, so I do this complicated thing to it, and I call it the trace function. Why do I call it the trace function? Well, then I have to talk about SL2C character variety. So if you have a metric, then you can associate this monodromy representation. So the way I think about it is that if you have a surface, then there's different sizes and shapes of it, right? And one way that you can see this is by lifting to the universal cover, in which case you can get different sizes and shapes of the universal cover in hyperbolic space, okay? And so this is just abstract in algebraic topology area. So, and in this universal cover, if you move from, you do a base change of base point transformation, right? Then you can go from one cover, what are these called? Oh, I'm blanking. Fundamental domain to another fundamental domain, right? Will give you an isometry from this to that, right? And so changing base point is along a path in the fundamental group, right? So from here to here, will give you some kind of isometry, which is the same as PSL2R. Or from here to here, will give you a different isometry of the hyperbolic plane. Is that okay? I kind of goofed out. Everyone okay? So for every metric, you can associate this monodromy, and then you can lift to SL2C instead of PSL2R. There's a whole bunch of algebraic geometry there. So because this character variety is a character variety, it's preferable in many, many ways, right? R is better, C is better than R. And so we look at this SL2C character variety, but in my head, I'm thinking only of the part where it's Teichmuller space, this algebraic sobriety. That's the part that I care about. And then there's all this other stuff that are SL2C stuff. right? But probably I shouldn't say that. Anyways, so if you have RSL2C, right? So these are representations of the fundamental group into SL2C. What can you do? You can take the trace, right? And then in fact, I could put a minus sign in front for technical reasons. And it turns out that on this, on the Teichmuller part, it's exactly the same as e to the minus length over 2 minus e to the minus L length over 2 on the other side. So something about the eigenvalues tell you the lengths. Okay, all right. So these trace functions generate the algebra of regular functions on the character variety. And the key aspect here is that they satisfy a skein relation. And the skein relation comes from a matrix identity from SL2C with trace of M, trace of N is the same as trace of Mn plus trace of Mn inverse. And it's kind of like this picture, right? Trace of M, trace of N, and then Mn and Mn inverse, but there's extra cases. So the proof isn't as easy as I make it sound, but it's not that much harder. So the skein relation is cool. And in particular, the skein relation has q to the half equals -1. And if you remember, that's when the skein algebra is commutative, where over and under doesn't matter, which makes sense because when I'm thinking about the fundamental group, I don't think of it as thick anymore. And so there's no room for crossings, over and under crossing. So everyone is over and under is undetectable when when I don't thicken it up. Anyways, for q equals 1, it was shown by Bullock, Fomin, and Konya-Bratosinska, and Persitsky-Sukra that there's an isomorphism from the skein algebra with q equals 1 and the SL2 algebra of functions on SL2C character variety. And it's really just matching k with the trace of k. And I think the proof was just using the trace identity in SL2C in the correct way. And so from here, so this is super exciting, right, for us, like from the hyperbolic geometry, because here's the skein algebra, here's the hyperbolic geometry. And actually, it's even better. These two are commutative. And so when q is not equal to 1, I kind of want to think of it as a non-commutative version. And and this was done by Turaev. So this is, I think, where the q equals 2 pi I over h comes in. If I take the commutator, then one's KL and LK over versus under, and I take the difference, I get some q times this minus q times that. If I now plug in e to the 2 pi I over h, I'm going to get something nice. And this something nice says that I get the leading term is 2 pi I h, and then there's this stuff. And then there's some higher order terms in h bar, but this stuff turns out to be exactly the Poisson bracket on that was computed for the algebra of functions on Teichmuller space. And so by Turaev, we now think of the skein algebra as a quantization of the SL2C character variety, but really I think it's a quantization of Teichmuller space. Okay, because Teichmuller space sits in there. Okay, and this correspondence can be made even stronger. So there's a very recent theorem that says that if q is a primitive root of unity and n is odd, then you can associate the representations with irreducible representations with points in the character variety. There's some extra stuff about data about the punctures that I have to include. So technically it's representations for a pair character variety plus puncture weights. There's some numbers I have to assign to the punctures to make this work. And so what happened, so with Francis Bonahan, we constructed left to right, and then we constructed right to left, but we couldn't prove that it was 1-to-1. And so that's Fomin, Kanya, Bartosinsky, Lay, and Ganev, Jordan, and Safronov said that it's 1-to-1 because of algebraic reasons. This is where that whole Osmaya stuff came in to show that this is actually, this works. Let's see, so to go from right No, it's like on my arrows wrong. So you go from left to right. Sorry, the arrow should go the other way. So if you go from right to left to right, so if you start off with a representation, then you want to essentially compute its central character, right? And so if you know the central characters elements here, that's this whole Chebyshev operation that I was talking about. For every k in here, you thread by a Chebyshev and it spits out something central. And you know those things generate the center, then you get some central character. And the central character, because of the previous page, is exactly a point in the character variety. Okay, did I say that too fast? Because in the not previous page, this one, right? Because now I get a central character and then that corresponds to a point in the character variety. Okay. These puncture weights are something that having to do with making sure that the loop around the puncture, like when you thread it with the Chebyshev, that it behaves nicely with everyone, like that. Because the puncture loop itself is central. So then when you thread it with the Chebyshev, it's also central. So you want to make sure that that all works out. So, okay. And then in the other direction, okay, so from here, I can reconstruct an irreducible representation here. And there's an explicit way of doing this. Using Chekhov-Falk algebra, and then there's a quantum trace map that maps the skein algebra to the Chekhov-Falk, and then Chekhov-Falk algebra, whose representation theory is easy, and you just kind of do that. It's explicit. I'm not going to say very much there because it goes on for a while if we wanted to go in that direction. Yeah.
May I ask a question? On the left-hand side of your isomorphism, I see how Q can play a role in defining the structure of the algebra SQ sigma. How does it show up in the right-hand side and the character there?
Yeah.
Where Q appears?
Oh, that's a good question. So for one, this only works when Q is an nth root of unity. And the n is this n from the Chebyshev that'll give me the central elements. So that appears there. In constructing, so in that direction, that's one way. In this direction, it turns out that when I construct these characters over there, I have to factor through the Chekhov-Falk, and then there's nth roots involved and lots of factors of Q in there. So that's hidden in this quantum trace map that I haven't talked about. Question. I'm sorry, I don't have a more satisfying answer.
Understanding what you're just saying, the right-hand side there does not depend on Q. It's the map that depends on Q back the other way.
Yes, I think. I don't know. It's hard to think on my feet, but yes. Anything else? Oh, the other thing that's interesting is that the dimension of the representation space, it's fixed for all of them. So the representation size of the representation spaces is the same, but like the metric changes where the matrices go. Right. And so that's kind of cool too. Okay. Any questions? Okay, I'm gonna now move to the second half. I don't even know if I have enough time for a second half, so we'll see. All right, so that was the story for the regular Teichmuller space. And what I'd like to do is to kind of mimic the same thing for decorated Teichmuller space. And this was really pioneered by Roger and Yang. So the decorated Teichmuller space is just like the regular Teichmuller space, except that at every puncture, I'm going to add in this horse cycle. So really just think about drawing a circle right there. Okay, and you can draw circles of different sizes you can choose. Okay, but you choose one circle, one horse sphere for every puncture. And why is this good? Well, this is good because now if I have something that stays in this middle part, so it's a loop, then I can compute length just like I did before. But now if I have an arc that winds around, that goes from puncture to puncture, I can chop it off here and also have a length of arcs, right? So if I have, right, so technically, if I don't put these Hor spheres, the length is infinite. And so putting the Hor sphere chops off the infinite part. And now I can measure the length from Hor sphere to Hor sphere. That gives me a length of arcs. And then this is kind of weird to think about. I also have a length of the vertex, which is just where did I chop it off? How big was that circle when I chopped it off? So there's a length of Hor sphere here. And so now I can compute lengths of loops, arcs, and punctures. And let's see. Then there's all sorts of different cool things that happen. So this was decorated Teichmuller spaces due to Penner. And Penner showed that if you look at an ideal triangulation, so that's a triangulation where the ends of the arcs go to the punctures, right? So these edges are arcs. And then you look at the lengths of them. So again, I'm doing this funny like business with the lengths, right? Where I take e to the length over 2 plus e to the minus lengths. So these, instead of giving trace, I'm calling these lambda lengths for historical reasons, or Penner coordinates, that these lambda length functions now generate the algebra on the decorated Teichmuller space. And you only need the edges of the triangulation to do this. The lambda lengths of the edges satisfy a Ptolemy relation. So if you change one edge to the other, you do a diagonal exchange or a flip or whatever you want to call these, a Pochner move, then the lambda lengths satisfy a really, really nice equation. Okay. And this is called the Ptolemy relation. So instead of skein relation, now I have Ptolemy relation. There's a Weil-Petersen-Poisson bracket, just like before. There's a computation using Mondello that Mondello did using these lambda lengths. Okay, so Roger Yang at this point was like, okay, I want to do the same thing as before with the quantum Teichmuller space, but now for decorated Teichmuller space. And so he looked at all these. So now instead of just a trace function of a loop, you have arcs and punctures. And he looked at the hyperbolic geometry, and they found all sorts of relations. And so based on these relations, they kind of conjectured that they were all of them. And they used these relations to come up with skein relations. Okay, so that mimic the skein relations over there. Okay, so let me define it. Any questions before I launch into, I'm going to go back to quantum topology. So anything about the hyperbolic geometry? Okay, so skein, so now they basically, the definition should look almost exactly the same, and it is almost exactly the same. So you still have a character q, except now instead of q to the half, I need q to the quarter as well. And again, I look at all the framed links, right, frame knots, but I also include arcs as well. So this is the generalization, we'll include arcs. And you have the two previous ones. These correspond to the skein relation for the trace functions or the lengths that correspond to the lengths of loops. And then you have these other ones that correspond to the, oh no, I have a lot of typos. There should be a V here. Let me write this down because this is a big chunks there. Okay, so it should be, so if this is the ith puncture, if I want to resolve this, this is equal to 1 over VI, q to the 1/4, and I can't remember which way. I think it's this one. The thing that I forgot is this thing here, which is super important because it says that the length of the Hor sphere makes a difference when you resolve crossings of arcs that end at that Hor sphere, right? Which kind of makes sense, right? If you have things going out into the same end, then where you chop off probably matters. And so anyway, so this was a big mistake. And then there's also, if you have a loop that goes around the puncture, then there's some number which is very similar to that, but only halves. Okay, so this is a different, so they came up with this, and I don't know, I kind of think of these as half crossings, right? So this is a full crossing and this is a half crossing. I should use this one, right? So, so on the regular one, to get q to the half, I make a left turn. From the bottom, I make a left turn. And for over here, I make a left turn at the half crossing, and I get this one as well. So everything is kind of like half as much as before, which kind of makes sense because like the formula is also half the formula of the lambda lengths, right? You only take half of it anyways. Okay, so just to be clear, so here I have the product of a loop around one of the handles and an arc that starts and ends, kind of crosses at a puncture. So this is a crossing that occurs at a puncture. And so I can, if it's in the middle here, then I can use the regular skein relation. So I get q to the halves and the two resolutions. And then I can also resolve the crossing at the puncture, and I can go either of two ways, and then I get q to the fourth in either of the two ways. Any questions about the definition? Make sense? No? Yes, okay. So Roger and Yang, they proved, basically looking to mimic the thing for the construction for the quantum, for the regular Teichmuller space. So if q equals 1, for every loop, instead of originally you send it to the trace function, now you send it to the lambda length function. And then there's also this plus or minus that drives me crazy, but you just pretend it's a plus or minus. I always pretend it's a plus. And then if you let it move off of 1, right? So if you think of q as not equal to 1, then you can think of their skein algebra as a deformation quantization of the decorated Teichmuller space. And this Poisson bracket that they use is the one the formulas come from the computation from Mondello. And this almost says that the skein algebra, that their skein algebra is a quantization of decorated Teichmuller space. Do you see what the problem is? There's one thing missing. So there's a map from here to here, but they don't show that it's injective, right? So this is what I said, where they said that these relations that they got, they think it was all of them, but they didn't know that it was all of them. If they knew that those relations were all of them, then it would be exactly the quantization, right? And so they needed that this phi needed to be injective for it to work, for it to be a quantization of the decorated Teichmuller space. And that's what I proved with Han-Bom and the papers on the archive. And so as a corollary of it being injective, you get immediately that it's a deformation quantization. Okay, so it's just kind of the same story generalized. The proof that we use is kind of interesting, perhaps for the algebraists. So what we do is that we couldn't show, so we've showed injectivity by appealing to a different arc algebra based on decorated Teichmuller space. We based it on the cluster algebra of the surface, right? And because the cluster algebra of the surface has these nice properties, we compare the Roger-Yang with q equals 1, which is also commutative, with the cluster algebra and show that they're compatible. And because they're compatible, then we could show that phi is injective, right? So a corollary of this is that the skein algebra is also a deformation quantization of the cluster algebra. And I don't know how interesting or not interesting this is. So the cluster algebra by itself, you can't use it's not easy to compute the quantum cluster algebra in the sense of Berenstein-Zelebinsky because of technical reasons. And so this gives you a quantization of that cluster algebra, but it's not quite, I don't know if it's exactly what the cluster algebra people want. Right, so I can explain, right? So in a quantum cluster algebra, you want that the cluster algebra is Q-commute. And here in the skein algebra, they don't Q-commute. You have a skein relation, there's two terms, right? And there's a Q to the half and Q to the minus half, or Q to the quarter and Q to the minus quarter, and there's a plus sign in there. So it's not exactly, but it's something. Okay, do I have time? How much time do I have left?
About 5 minutes.
Okay. Can I do a real brief sketch of the proof? I'm going to pretend like you guys know what its cluster algebra is. If you want me to explain it, I put some slides at the end and I can explain how that works. Okay, so the sketch of the proof goes like this. It's a lot of algebra. So if they, so the map that they look at sends any not loop or arc to its lambda length, right? So that's the map that Roger Yang said was well defined. And if you allow the edges of an ideal triangulation to be invertible, then you can there's a localization gives you an injection. Okay, so into the algebra of functions. And this, I mean, you're looking at lambda lengths, so everything works out fine. And moreover, if you have no zero divisors, then this localization map is injective. So if I can show there's no zero divisors, then I can go from skein algebra to the localization up to the algebra of regular functions of the decorated Teichmuller space, and then I'm done. Okay, so it's pretty easy algebra so far. We tried very hard in an earlier work to show that the skein algebra had no zero divisors. This is kind of the same thing as saying that the skein, the skein relations aren't like that Roger Yang had kind of makes sense, right? And when the surface has a nice triangulation without self-folded triangles, then we could like draw a ton of pictures and say, oh, the combinatorics works, right? But then as soon as we have these self-folded triangles, we were just like tearing our hair out. We just couldn't do it. Not that it was just combinatorial too hard. So we kind of gave up and we wrote the paper, and then we said we needed a new idea. And the new idea was this cluster algebra. And the idea is that this, we look at the cluster algebra of the surface. It has no zero divisors, right? So we know it's nice. You show that there's an embedding into the skein algebra, which kind of, if you think about it, makes sense because the cluster algebra only deals with edges, meaning arcs. And so, but over here, it's kind of the same stuff, gives you loops, arcs, and vertices, right? So definitely it's going to be, you just kind of map it over and it's kind of, you just check that it works. Then we kind of want to show that because the skein algebra, I mean, the cluster algebra has no zero divisors, then the skein algebra doesn't have any zero divisors. And you just kind of make it bigger until it matches. Okay, and this is because the skein algebra is finitely generated. I showed that with a bunch of undergraduates that I had, so it's not very difficult to do. And you kind of keep track of the dimensions and make sure everything works out. Then you can see that when you extend the cluster algebra, so you add in extra stuff into it, that it corresponds to the skein algebra.
I'm puzzled by that equality of dimensions. I mean, aren't these infinite dimensional?
No, not as algebras.
They're finite dimensional algebras.
That's right.
So,
Oh, wait. Finite dimension in the, I think this is in the algebraic geometry sense.
cruel dimension.
Pardon?
Cruel dimension.
Yes, cruel dimension. That's right.
Okay.
That's right.
Okay.
Thank you. Other questions? And so then I get that.
Well, I did have one other
Yeah.
question. What's that top right corner of the diagram?
Oh, this is the field of fractions,
Oh, just
the rational functions.
and several
Right.
variables.
Yeah.
Yeah. Okay.
So like the cluster algebra definitely is inside the rational. There's another, and because these are all lambda length functions, you can kind of think of the lambda lengths as the e to the i's. And so there's also another, and there's a way to do that as well. Okay. And that was the end of the proof. And if I don't think I have time, but if you want, I can talk about what a cluster algebra is and how to embed one into the other. But questions, do I have time? You can ask me about it and then I can, and then I can answer.
So what about offering the time to questions and then discussion
Yes.
in front of a coffee? So questions. Loïc, and then Kaveh, fetch your microphone, Kaveh. Loïc first, but Kaveh.
Okay, so the skein algebra, the first one, was related to the Jones polynomial.
Yes.
So the new story with the decorated Teichmuller space and the Roger Yang algebra, is it related to something for knots and links?
We don't know. So there's no like Kauffman bracket that we know of that, or Jones-Paul invariant that is defined. In the WittenReshetikhin-Turaev theory, the manifolds are always either with boundary or compact, no boundary, but there's like the punctured ones, it's not obvious what the role is of that. And so we don't know.
Something which a little bit reminds me of that is the singular linked theory.
Oh,
links with
yes.
singular crossings.
So I don't know. Yeah,
Probably not.
maybe.
Yeah.
Yes, exactly. So I think that would be a great research topic. So this new one is 2014. I should say that Muller also has a skein algebra for surfaces with boundary, but then you need marked points on the boundary, so that tells you where the arcs can end. And that also is related to cluster algebras. But I think for that theory is kind of like is easier to put together, because if you have boundary, you can kind of take two surfaces with boundary and glue them together if the boundaries match. When there's punctures, kind of know how to, it's just this weird thing that is always an exception.
At the beginning of the sketch of your proof, you kind of related the data you wanted to analyze to the arcs on the surface, which now play the role of cluster variables.
Yes.
Does it matter from which cluster you begin the arguments? Because like different triangulations would result in different clusters, and
Yeah.
like the proof is completely independent
It's
of
completely independent.
the initial cluster. Okay.
I'm going to use this as an excuse to page through. All right. So when you have punctures, then you can't just use regular edges. You have to use this thing with taggings due to Fomin, Shapiro, Thurston. And so, so this tag, kind of from the geometric point of view, we didn't know what it meant. And so the algebra homomorphism is that the tags correspond to a choice. So if you have a tag, you put a V in front and a W in front if you have a tag at W. And so those taggings correspond to like the length of the Hoare cycle around that puncture. Okay, so, but in any case, from this definition, it works for any edge. So any arc, even if it has crossings, it doesn't have to be an edge of an ideal triangulation. So, but if it is an ideal, wait. Cluster variables only are ideal triangulations, right? So from these edges of the ideal triangulation, you can map it into the skein algebra where you have many more different kinds of arcs than.
That's what was partially I was wondering about is for the cluster structure, you try to avoid any intersection by the nature of the cluster structure. Does that manifest anything at the level of the argument you're trying to prove?
No, so so this map is just checking that it works, right? But you could, like you say, on the cluster of variables, there's no crossings, and because everything is within each cluster, it's an ideal triangulation, whereas in the skein algebra, it's a free-for-all, right? Arcs can do whatever they want. And so, okay, so I'm gonna say something that Han-Bom will probably complain about, but here's something that we think is that, so Han-Bom thinks that there's this A here, and on the other side is the upper cluster algebra, is bigger or somewhat related to the skein algebra. So there's the image of this in here, and we think that the image is inside the upper cluster algebra, but because of these vertex classes, which don't exist in the cluster algebra world, the skein algebra is like this, and the cluster algebra is like the upper cluster algebra is like this, and they're not exactly the same. So there's some kind of issue here. But what Han-Bom wants to do is, this skein algebra is nice for all sorts of reasons, like the algebraic structure is like, for example, we know it's finitely generated, and for some small surfaces, we have a presentation. So can we say things about whether the cluster algebra is finitely generated by kind of going backwards?
So I invite any further question or discussion to be held within the coffee break.
Thank you.
Thank you very much.
Thank you very much.